In the proof of the completeness theorem, we saw that if we work with a consistent theory over a countable language, then we could construct a countable model. One can now ask, given any infinite model, can we find a countable elementary submodel? So for example, we saw before in the previous lesson that Q, the linear order of Q, is a countable elementary submodel of the linear order of R. Right? So in general, is finding something like that possible? Well, if the language is too rich, then this might not be possible. For example, we could have elements in our language, an uncountable language, with a lot of conditions like C is not equal to D, right, in the theory, where these are constant symbols, right? And if there are a lot of them around, in particular uncountably many, and the theory tells us that they have to be different, then they cannot be a countable model. But as we will see, that's pretty much the only restriction that we'll have. So here's the statement of the corresponding theorem, called the downward version of the Löwenheim-Skolem theorem. If A is an L structure and kappa is a cardinal at least as large as the cardinality of the language, on the previous slide I gave a little bit of an intuition why we need to require that, because otherwise we could formulate a lot of requirements in over a structure that would be impossible to meet with a cardinality, structure of cardinality less than the cardinality of the language. And we also have that the cardinal kappa is at most the cardinality of A. Then there exists an elementary substructure of A of cardinality kappa. The basic steps of the proof of this theorem are as follows. We start with an arbitrary subset of the universe of A, so call that A0, and that A0 has cardinality kappa. So this is really arbitrary, so we could actually include this in the statement of the theorem that not only can we find an elementary substructure of cardinality kappa, but that elementary substructure could actually extend any subset of A of cardinality at most kappa. Okay, so we fix that, we start with that, and now what we try to do is to construct an elementary substructure. We try to satisfy the Tarski-Ward conditions, namely for any formula and tuple from A, right, with A satisfies this existential formula here, we have to add a witness to A0, so with that we can apply the Tarski-Ward test then. So suppose we do this extension, so we extend A0 to A1 by adding the necessary witnesses for the Tarski-Ward test. Well, that of course now adds new elements for which we can find new formulas of this form, which we can plug into formulas again. So we need to add, again, witnesses to existential formulas that hold for tuples from A1 now, right? From this A1. So we iterate, extending A1 to A2 by adding Tarski-Ward witnesses, and then that to, in general, from AI to AI plus 1, right? And we throw all of these then together into one big universe B, and we have to verify then that this B is actually a substructure. Not only is it a subset of the universe of A, but it's actually a substructure. So you need to verify that and then apply the Tarski-Ward test to show that this is actually an elementary substructure. Just as we can go downward in cardinality, there's a version of the Löwenheim-Skolem theorem, the upward version, that tells us we can find an elementary extension of arbitrary cardinality, given that that cardinality is greater than both the cardinality of the language and the cardinality of the structure. The proof of this upward version is a combination of the diagram method and the compactness theorem. So we start with by picking an arbitrary set that extends the universe of A of the desired cardinality. Now we take the elementary diagram of A. Remember that we were able to characterize elementary extensions by being a model of that elementary diagram, right? So we take that, but now we need to ensure that every model has cardinality kappa. So we take T prime to be the elementary diagram and throw in new constant symbols for C, right? And require that these, for every two elements in, or distinct elements in C, these constants are different. So we add that to our theory. Then we apply compactness, and possibly, because the compactness theorem doesn't really give us control over cardinality yet, so we possibly have to also apply Löwenheim-Skolem downward. So try to fill in the details for these steps. It's really not too hard. As a consequence of these two theorems, we now have that if we have a consistent theory T that has an infinite model, then that theory has indeed a model of every cardinality at least as large as the cardinality of the language. So we not only have countable models if, for example, the language is countable. If we have an infinite model, then we also have models of every infinite cardinality.